Hello, everyone. So we have another question. This was a interesting ARML problem. So before I do this problem, I just want to remind a actually nice relation which we call Mendeley's theorem to actually use in this problem. So this was a tiebreaker problem. Okay, so in the ARML test. So let's kind of start with a triangle just to define the Mendeley's theorem. So we start with a triangle. Okay, and let's call this as ABC. And we are going to take 2 points. I'll say let's take 1 point right here, and let's say 1 point right there. So I'm going to call this is D. And this is E. So basically, we choose 2 points on two sides of the triangle, and the third side is BC in my case. And then we're going to extend this. And then when you extend this BC, and if there is a line that you can draw through DE and the intersection of that line BC, which we will draw. So based on my points I chosen, so I will probably get something on this side. So let's go ahead and extend that line. Okay, so if I extend this, I will probably get something like this. And then if I extend BC, so they will intersect at some point. And then this is the condition where we actually can use the Mendeley's theorem. So we start with 2 points on the sides, and the third side will be also having 1 point, but it's not going to be on the side. It's going to be just extension of that side. And then when this happens, we do have a relation. The first thing is, this is the point outside of my original triangle I start with. I start from this point all the way distance from that point to the side BC, which is the point B. So you start with F, B, over. So this is from F to C. Okay, so that is FC times, okay, that the ratio will be multiplied times, we are going to take the point C, which is the first intersection, from C to the other intersection, which is EC or CE, divided by the remaining part of that segment, so which is AE or CA. And then we multiply this by the AD divided by BD. AD, which is this distance, divided by BD or DB. And then when you multiply all these, this is going to be equal to 1, and that is called Mendeley's theorem. So it looks like a bit interesting, a bit challenging, and then I'll say it's going to be a bit harder to kind of see in every question. So I'm going to kind of add some question in the description so you can actually practice with those just to feel better. But let's remember this as our kind of note, and then use this problem to apply this Mendeley's theorem. Okay, so let me clear this first. And then we have a parallelogram. So, and then ABC is the obtuse angle. So I'm going to say maybe we have something like this. Okay, so I'll try something like this. And since B is the obtuse angle, so I'm going to take this one or this one. So let's take this as A, and then this is B, C, and D, right? And BE is the altitude of the side AD. So B is right here, so we drop the altitude, I guess, that way. So that is BE. Okay, and then of ABD, X is the point of intersection of AC and BE. So like this is BE, and then this is A and C, so we'll have the diagonal AC. And then intersection is named X. Okay, that is X. And then F is the point of intersection of AB and DX. So the AB is right here, X right here, D right here. So we should extend DX to get that intersection. So it will look like this one. And then this is called F. With that in mind, so we have some numbers, and we want to find the AC, which is the diagonal, divided by AF. Okay, so AF in this case right here, and then BC, CD is given, CD is 13, BC is 30, and BE is like this height is 12. This is BA, which is also 13 because of this, and then this is 12, so he uses Pythagorean triple or Pythagorean, that's 5 immediately, since this is 30, so I will get 25 for ED as well. And the first thing I can see, because we want to relate AF and the diagonal somehow, right? So we just need to maybe connect B and D, because that will make two equal pieces of AC. So if I can find only this part, so I can find the remaining by doubling. But maybe before I draw that, so I'm gonna show you something right here. So the triangle right here, the first thing that is kind of obvious right here is similar to the triangle right here, because angle similarity. So, and the ratio is 5 to 30, so that will be useful, I guess. So that will be 1, and then this will be 6. 5 to 30 is 1 to 6. If I call maybe this is like K for this part, entire thing will be just 6K. But at the same time, I don't want to use 1 and 6, because when you connect B and D, this midpoint will split the AC into 2 equal pieces, but AC in total is like 7K. So I just don't want to do that with fractional number when I take the half out. So I'll just say this is, let's say, 2K. That means this is going to be 12K. So if I take the BD, that will make the half of the entire AC. So again, this is 2K, and then XC is going to be 6 times, which is 12. 12 plus 2 is 14. So that means this is 7K, and then that will be 5K. So we'll use that if we need to. And then we just need to relate the Ks with AF somehow, right? That's what we are interested. And let's go back to remember our, I guess, Mendeley's theorem. So when there is a triangle, so think about this triangle, AE, AEB, this triangle has actually 2 points on this side. So this is 1 point, and then this is another point. And the third side is AE. When you extend this, there is a point D right here. So you can just kind of see it, that is going to be a straight line as given. So we can use the Menelaus theorem in this problem. So if you remember, the first thing we have is we start from the outside point, which is D, and then take the distance from that point all the way to the side that is not have a point on that segment. So the furthest point from that outside point, so which is DA. Okay, over from this point to the other point on that segment, which is E. So you will get DE. And then multiply this by, as soon as we hit this point E, so you just go from here, so the E to X. So the EX over X to B. So that is XB. And then times the BF over FA. And then this product is going to be 1. So we know DA is 20, like 5 plus 5, which is 30. And then DE is like 25. And then EX right here and EB, we did have this ratio because 5 to 30 was 1 to 6, which means EX to XB is also 1 to 6. So this ratio is 1 over 6. And then times BF over FA is 1. So I can easily cancel this. That should be 5. And then this cancel, that will be 5 and 1. So this is 1/5 times BF times FA. To get this one, BF should be 5 times FA. And I do know AB was 13, so the AF is going to be 1/6 of that AB. So then I can just say AF is going to be 1/6 of 13, so which is 13 over 6. Okay, so we know the AF, which is good, but we don't know the AC. But we actually can use the Pythagorean because we can kind of try to make a right triangle. So if I draw this altitude and connect with this one, so we have a right triangle going on. So that should be right here, 90 degrees. So this is 5, so that will be 5. And the height was 12, so this is also 12. And then this leg is 35. This is 12. If you use the Pythagorean, so 12 square and 35 square, so that should be AC squared. And then you can use the Pythagorean to get the answer, so which is going to be AC. But if you feel like you remember some of the Pythagorean triples, 12, 35, and 37 is actually a triple. So you can get that immediately without going through the Pythagorean. So that should save some time. So AC is 37. And I know AF is already known as 13 over 6. And then AC is 37. So the ratio that is what we are interested in is 37 over this number. So you should get 13 over 6. And then that is 37 times 6 over 13. It doesn't look like we have anything we can simplify. 6 times 30 is 180. And then 6 times 7, 42. So 180 plus 42, it looks like 222, right? Over 13. And then that is the segments we were interested. So that is our answer. I hope that was clear. So again, as I mentioned, so I'm going to add some problems in the description to use the Menelaus theorem. So you can try those as well. But to be honest, we can use the Siva's theorem in this problem as well, or even just using the similar triangles, and you can still get the answer. But I'm going to leave those approach for you to try. But I just want to show you the Menelaus approach at least for this video. Okay, I'll see you in the next video.